With the rise of cell phone cameras, selfies, or direct images of an individual's face have become increasingly popular. Champion among the selfie application is Snapchat, which allows users to take images and videos of themselves and share them with friends. To continue to draw interest to these applications, unique filters and exclusive face effects have been added. To compete with Snapchat and other similar companies, we have created FaceSwap3. Our product uses an extremely fast detection method to find key facial features and then allow the user to swap faces with another friend in the frame or with a saved picture. Also, we've included a few interesting color filters to distinguish ourselves from our other colleagues. The FaceSwap3 product works well with face swapping videos and pictures and creates an easy user experience with basic key commands to switch functions. The face is quickly detected and smoothly passed to the other person. Here, we have a few example videos of the product. First, the face swap itself is demonstrated. The swap smoothly switches the two faces with each other and is preserved despite large amounts of movements. The two face swap fairly seamlessly, with color blending near the edges. Our next key feature is the color filters, which allow our user to change the general color of the scene and still use the face swap functionality. We're also able to use the facial features to create creative masks and switch with other images of faces to perform the unique swaps not normally available. In running the code, we have a number of key commands that will call the swap code and various filters, finally returning the processed image and grabbing the next frame, repeating the process until the exit key is pressed. The highlight of our code is that the face swapping algorithm, which works by detecting faces and features in a frame, performing an affine transform to move the face, applying a mask around the key points of the face, and finally merging the frame, transformed faces, and masks into the output image. The most important part of our algorithm depends on identifying faces in an image and marking key face points, such as marks around the eyes, nose, and mouth. To do this, the C++ implementation of 1 millisecond face alignment with an ensemble of regression trees was used from the dlib library written by Davis King. The basics behind the code use a histogram of gradients, a linear classifier, an image pyramid, and a sliding window detection scheme. The process itself is very unique and interesting to research, but Davis King has provided a simple open source code format to train from a set of data to find the faces in an image and return 68 mark points around the structure of the face. Once the 68 points have been found for all the facial features, the next step is to move the face from one person to the other. To do this, we calculate an affine transformation matrix, which allows us to figure out the rotation, translation, and scaling needed to match the key points together. The affine transform works by taking 3 key points and matching them to the same points in the other faces. By using only 3 points, we preserve parallel lines in the plane of the face, rather than distorting the face to fit the mask, as sometimes seen with the perspective transform. With the key points located around each face, we want to mask out the original face and replace it with the new transform face. Given the list of facial features, we want to grab the extreme points and find the connecting shape, called the hole. To compute the outermost boundary, we use the function cb2 convex hole and create a mask where the face was 1 and the outside was 0. Next, to better smooth the structure together, a Gaussian blur was applied to the mask, expanding and reducing the values at the edges of the mask. This blur of the colors of the two faces together, creating an almost seamless blend. Once the mask and affine transform have been calculated, the mask is applied to the transform to get the newly positioned face, and the opposite of the mask is applied to the original frame. The process is repeated for both faces, outputting the final image of swapped faces. Next, our other key feature is color filtering. For the color filtering, we took the RGB frame and converted it to LAB space, which preserves the luminance important data, but allows us to mess with the A and B color directions. To change color, we attempt to match the A and B data to a chosen sample image, such as the pink candy for a pink result, a blue whale for an underwater blue effect, and a green garden to change the scene to a brilliant green. The image is then converted back to RGB space and displayed. So now that the basics of the FaceSwap3 algorithm have been laid out, let's take a look at our main competition, Snapchat, and how we stack up. Here's an example of the output given by Snapchat, which also provides a smooth face swap in real time. Looking at our output results, we are successfully swapping faces in a 640 by 360 frame at 0.3 seconds for each frame. Snapchat currently has better results with a higher resolution based on the phone camera, typically around 720 by 1280, and processes at 0.033 seconds per frame, or a typical 30 frames per second. So while FaceSwap3 was not quite an optimal real-time, the slowest part of the code is actually the dlib library transferring the data from C++ to Python. By switching to a full C++ implementation of our code, we are confident that the resulting outputs of frames would be nearly 0.033 seconds. Also, due to the training of the face detection, the algorithm looks only for direct faces. Snapchat is only able to process vertical videos, and we are only able to process horizontal videos. Upside down, angled faces, and side profiles all get lost since they aren't in the training data and obscure or move the notable features. By expanding the training data and adding more classifications to look for, we could potentially swap with more orientations of the face. Some of the problems with Snapchat's algorithm is that it's not constantly recalculating the facial features, which leads to strange distortions and assuming faces where none exist. FaceSwap3 will constantly look in each frame to find the face, which leads to a more accurate swap, but also more losses of faces if it doesn't fit the training data or moves slightly out of frame. Occlusion of the feature points will cause a face to drop from the scene. Another way to try and reduce the number of points would be to have it perform an initial location of the points on the whole face and then reduce the number of points to just a few, for example the nose. Having these key points would help deal with some of the occlusion, but might lead to issues with the transform of scaling and rotating. Another couple of interesting areas to investigate further are new functions in the CV2 library. With the newest version of CV2, a function called seamless cloning will take a mask and images and attempt to blend them together, better matching the color and lighting of the original face with the swap. Also, rather than creating one mask, we could potentially break the mask into smaller triangles to better match each dot together, creating a much smoother switch. To conclude, FaceSwap3 as a product enters an exciting and growing market, allowing a user to perform unique image manipulation at the press of a button in a quick fashion puts us in a good place in the market. And plenty of interesting techniques exist besides face swapping that can still be developed. A potential idea is swapping face features such as the eyes with the mouth with the eyes, providing a strange Picasso look. Or calculating an average face between two people and replacing both faces with the new average. With a strong face detection code and fast real-time structure, FaceSwap3 looks poised to continue to grow and swap places with competitors such as Snapchat. If the product interests you or you have any comments and concerns, feel free to contact us. Thanks for watching.